Welcome to the next video in the series of discrete maths course. So first of all, I would request you that if you are new to the channel, please subscribe the channel and watch the videos in the sequential order. I have created separate playlist as per your requirement. So please watch the videos as per your need and requirement, but whenever you are watching the video of a particular topic, watch it from the beginning to end and watch it in sequence so that your concepts are clear. It is like if you just jump from one video to another video, possibly you may miss on some of the concepts. So let us start right away. So the first thing that we are going to talk about here is asymmetric relation and irreflexive relation. If you remember, in the previous video I talked about four kind of relation: reflexive, symmetric, antisymmetric and transitive relation. So in continuation to that, we are going to talk about asymmetric relation and irreflexive relation. So first of all, look at the definition. A relation R is called asymmetric if AB in R implies BA is not in R. Now if you look at the definition, it is slightly different from antisymmetric relation, because in antisymmetric also we have this requirement that if AB is in R, then BA should not be in R. But in case of antisymmetric relation, we have allowed those elements to be in R for which A and B are equal. But in the case of asymmetric relation, this is also not allowed. We are going to look at examples to understand it better. But before that, let us look at the definition of irreflexive relation. So a relation R on the set A is irreflexive if for every element A in capital A, the capital A is the set on which we are defining the relation, A comma A should not belong to R, right? It means that R is reflexive in if no element in A is related to itself. Okay, so let us look at the examples one by one. So look at A example. So first of all, whether A is asymmetric relation or not. So we notice here that in this 2, 3 element is there and 3, 2 element is also there. So it is not asymmetric. Even 2, 2 is there, which is also not allowed, because for it to be asymmetric, if A comma B is there, then B comma A should not be there, even though they are equal, right? So this is not asymmetric relation, right? What about the next one? Next one is also not asymmetric, because 1, 2 is there and 2, 1 is also there. So this is also not asymmetric. Here 2, 4 is there and 4, 2 is also there. So this is also not asymmetric. What about the D? Here 1, 2 is there, but 2, 1 is not there. 2, 3 is there, but 3, 2 is not present. 3, 4 is present, but 4, 3 is not present. So this is asymmetric relation. If I look at the fifth example, we have 1, 1, 2, 2, 3, 3, 4, 4, and for relation to be asymmetric, if A comma B belongs to R, then B comma A should not belong to R, even in case E and B are equal, right? So this is also not asymmetric. Now don't get confused. If I ask you whether it is antisymmetric, then yes, it is antisymmetric, because in antisymmetric we allow A comma A type of element. When A and B are equal, we allow those elements. But asymmetric relations are slightly more strict, right? So it does not allow A comma A type element also. What about the last one? Here we notice that we have 1, 3 and we also have 3, 1. So this is also not asymmetric. So only one relation here is asymmetric, and that is relation D. Okay. Now let us look at irreflexive property. So what about this? This one is not irreflexive, because we have 2, 2 present here, because for it to be irreflexive, all a comma a element should not belong to R. So here 2 comma 2 belongs to this, so that is why it is not irreflexive. Here also it is not irreflexive because 2 comma 2 belongs to this also. What about this? This is irreflexive. The reason is that here we don't have any element of type a comma a, so this is irreflexive. What about this? 1 comma 2 is there, 2 comma 3 is there, and 3 comma 4 is there. So there is no element like a comma a, so this is also irreflexive. Here this is not irreflexive because a comma 1 comma 1 is also there, 2 comma 2 is also there. Even though if one of them is present, then it will become irreflexive. Here more than one of the element of type a comma a is present, so this is also not irreflexive relation. And what about the last one? So last one, we don't have any element of a comma a type, 1 3 1 4 2 3 2 4 3 1 and 3 4. So this one is irreflexive. So here there are three relations that is represented by C and represented by the relation C and the relation D and the relation F, means C, example C, example D and example F. These are irreflexive. Let me write it in case if you are creating your own note. So these are irreflexive. And anti-symmetric relation was just one, so anti-symmetric was D. So D, not anti-symmetric, sorry, I beg your pardon, asymmetric, right? So asymmetric. Okay. So I hope with these examples you are clear about what is asymmetric and irreflexive relations. Okay, so now I'm going to define two important terms. One is inverse relation and another one is complementary relation. So how the definition looks like, what is the inverse relation? So let R be a relation from set A to a set B. The inverse relation is defined from set B to set A and it is denoted by R inverse, and it contains all the set of ordered pair of type B comma A where A comma B belongs to R. So to understand this, let us look at this example. Here we have a set A, and on this set A I have defined a relation which is given by this. So to define the relation on set A, I have first calculated A cross A, which contains these 9 elements, the Cartesian product, and I hope you understand how it is calculated. 1 1 1 2 and all those 9 elements are there. Now in this R we have element 1 comma 2, 1 comma 3, 2 comma 3, 3 comma 1 and 3 comma 2. So how the inverse relation will be defined? It is saying that if AB belongs to R, then BA belongs to R inverse. So if 1 2 belongs to R, then 2 comma 1 should belong to R inverse. If 1 comma 3 is in R, then 3 comma 1 is in R inverse. If 2 comma 3 is there, here we will have 3 comma 2. 1 comma 3, so here 3 comma 1, so here I will have 1 comma 3. 3 comma 2, so here I will have 2 comma 3. So this is the relation R inverse. Now the next term is what is complementary relation. So the complementary relation, which I represent by R bar, is the set of ordered pair A comma B such that A comma B is not in R. Now to find out this, let us take the same example. Here we have to write all those ordered pair in the complement of R which are not present in R. So here 1 comma 2 is present in R. Let me write it from here. This is 1 comma 1, because in A cross A we have 1 comma 1, so I am writing 1 comma 1. 1 comma 2 I can't write because 1 comma 2 is present, so I won't write 1 comma 2. What about 1 comma 3? So 1 comma 3 is also present in this, so I won't write 1 comma 3. What is 2 comma 1? So 2 comma 1 is not present in R, so I will write 2 comma 1 here. 2 comma 2, so 2 comma 2 is also not present in R, so I am writing 2 comma 2. 2 comma 3 is present here, so I won't write 2 comma 3. 3 comma 1 is also present here, so I should not write 3 comma 1. 3 comma 2 is also present in R, so I should also not write 3 comma 2. But 3 comma 3 is not present, so I am going to write 3 comma 3 in the R complement. So I hope you noticed that if I take R complement and R, I get the whole Cartesian product, that is A cross A, right? So I believe that you are clear about how to write R inverse and how to write R complement. Okay. Now let us talk about how to combine different kind of relation. And this is a very simple idea. I think most of you might already be aware about this, but just to be clear, I am repeating this. So we have two sets A and B, and on these two sets I have defined the relation R1 and R2, and suppose I have to combine them. So first operation is R1 union R2, and if I have to calculate R1 union R2, means I have to include all ordered pair which are either in R1 or in R2, right? So we have seen here that 1 comma 1 is in R1, so I am writing 1 comma 1, 2 comma 2 and 3 comma 3. So all those elements which are present in R1 is written here. 1 comma 1 is in R2, which I already have written. 1 comma 2 is there, so I need to write 1 comma 2. 1 comma 3 is there, so I also need to write 1 comma 3, and 1 comma 4 is there, so I need to write 1 comma 4. So this is the relation, that is R1 union R2. Now if I ask you that what is R1 intersection R2, so I believe that you can very easily guess that the common element which belong to both R1 and R2 will be there in R1 intersection R2, and one such common element is there, that is 1 comma 1. So in that a 1 2 and 1 3 and 1 4 are not present in R1, and here 2 2 and 3 3 are not present in R2. So we have just one element, that is 1 comma 1. Another operation that we can define is R1 minus R2. So though if you have studied set theory, you might be aware that in R1 minus R2 I write those elements which are in R1 but not in R2. So in R1 we have 1 comma 1, so I will write 1 comma 1. And 1 comma 1 is in R2 also, so I will not write 1 comma 1. Let me correct it, I made a mistake over here. What I am saying is that what is R1 minus R2 means I will write those elements which are present in R1 but not in R2. So 1 comma 1 is present in R1 but it is also present in R2, so I won't write it. What about 2 comma 2? So 2 comma 2 is present in R1, so I am writing 2 comma 2, and it is not present in R2, that is why I have written it. What about 3 comma 3? So 3 comma 3 is present in R1 but it is not present in R2, so I am writing 3 comma 3, right? There is no other elements in R1, so I am just closing it, and this is how we define R1 minus R2. I hope you remember when I define the subtraction of two set A minus B, I write those element X which are in A, X should be in A and X should not be in B. So that is how you define R1 minus R2. Similarly, if I ask you what is R2 minus R1, so in this case I am going to write those elements which are in R2 but not in R1. So 1 comma 2 is in R2, so I am writing 1 comma 2 because it is not in R1. 1 comma 3 is in R2 but it is not in R1. 1 comma 4 is also in R2, right? You can see, but it is not in R1, so I have written that. And 1 comma 1 is also in R2, but since it is in R1 also, I should not write. Yes or no? I hope you are getting that when I have to calculate like A minus B, if this is the set A, this is the set B, then I take only those elements which are there in this part, which are in A but not in B, means the common part is not being written. There is one more operation that we can define, and that is called the exclusive OR operator. So if I ask you what is R1 plus exclusive OR R2, this is defined as R1 union R2, right, and minus R1 intersection R2. You should remember this. So if I ask you what is R1 union R2 minus R1 intersection R2, so it is going to contain all those elements which are there in R1 union R2 but not in R1 intersection R2. So what is the value of it here? So R1 union R2 minus R1 intersection R2. So in R1 union R2 we have all these elements. In R1 intersection R2 we have just one. So I will write 2 comma 2, 3 comma 3, 1 comma 2, 1 comma 3 and 1 comma 4. Right. I have to remove that element which is present in R1 intersection R2. So we have defined what is R1 union R2, R1 intersection R2, R1 minus R2, R2 minus R1 and R1 exclusive or R2. Now we are going to look at the composite of relation thing, and to understand the composite of relation thing you have to understand this picture, that suppose we have two sets A and B, right, and from A to B we have defined a relation which I am representing by R, and from B to C I have defined other relation that I am representing by S. So the composite of R and S, which I am representing by S composition R, means we are taking R first and then we are taking S. So that is the relation from A to C, right? So if you look at this, we have to understand it this way, that first the relation R is used, and once I decide that okay, R is taking a particular element to a particular element, then how this S will act over it, right? So to understand this, let us take this example. So we have a set A which is given by 1 comma 2 comma 3, and we have the set B which is given by 1 comma 2 comma 3 comma 4, and we have the set C which is given by 0 comma 1 comma 2. So a relation is defined from A to B. That relation we are calling R. So first understand, R is defined from A to B, and this S relation is defined from B to C. So this composition that I am representing by S composition R, it will be defined from A to C. That you should be clear about. That first R is acting. It should be seen like this, that first R is acting. So R is going to take the elements of A to the elements of B, and then S is acting, which is going to take the element of B to the element of C. So if I ask you that what is composition of R and S, then this is how we are representing it. And you see here in the R we have the element 1 comma 1. So this 1 is going to 1, and here this 1 is going to 0. The element, the relation R is taking the element 1 to 1, but the element of this relation S is taking the element from 1 to 0. So ultimately 1 is going to 0, right? Now if you look at this element, 1 is going to 1 and there is no other element which is starting from 1 here. So now I will move to the next element, right? So in the next, 1 is going to 4, right? 1 is going to 4 because R is taking 1 to 4 and S is taking 4 to 1. So 1 will ultimately go to 1, right? Now there is no other element which is starting at 4 here. So I go to the next element, that is 2 comma 3. So here 2 is going to 3, right? By this this relation R, 2 is going to 3, but 3 is going to 2 here. So ultimately 2 is going to 2, right? Now 2 is going to 3 and 3 is also going to 1. I also have to look at that 2 is going to 3 and 3 is going to 1. So 2 is also going to 1. 2 is also going to 1, right? Let me rewrite it for better understanding. 2 is also going to 1. So 2 comma 1 will be there. Now 2 is going to 3 and I already have taken this 2 possibility, that 3 is going to 1 and 3 is going to 2. There is no element which is taking 3 to some other element. Now I take 3 comma 1. So 3 is going to 1 and 1 is going to 0. So here 3 will go to 0, okay? And 3 is going to 1, and is 1 going to somewhere else? No, 1 is not going to any other place. So I will just write 3 comma 0. And if you look at this 3 comma 4, so 3 is going to 4 and 4 is going to 1. So 3 is going to 1, right? This is a comma. It should be seen as a comma, and this is the element 1. Now is there any other possibility? I think we are done. We have elements like 1 comma 0, 1 comma 1, 2 comma 2, 2 comma 1. We can write in 2 comma 1 and 2 comma 2. The order is not important in a set. And then 3 comma 0 and 3 comma 1. So I hope you have understood the composition part. I repeat this thing. When I am defining the composition, suppose the relation R is defined from A to B. So the elements of A are going to elements of B. Then if the relation S is defined from B to C, so the elements of A are being taken to the elements of B by the relation R. So R is acting first, and then we are applying S. So S circle R, or this is how the composition should be read, that we are writing it the composite of R and S. We are looking at from the right, composition of R and S. So it is defined from A to C. It is defined from A to C. And how it is defined? So if there is an element A comma B in R, and there is an element B comma C in S, if there is an element A comma B in R and B comma C in S, then in the composition of R and S, the element A comma C will belong. So how it is like working? A is going to B, that is because of R, and B is going to C, that is because of S. So first apply R and then apply S, then A will go to B and then B will go to C. So ultimately A comma C will belong to S composition R. I hope it is making sense to you. Now let us look at this particular problem to understand that how the composition works. So before that, let us see this small definition, that let R be a relation on a set A. Now I am defining the relation on one particular set. In earlier I was defining it from set A to set B. Then I can define the power of Rn, means R to the power n, and this is how it is defined. R1 is equal to R, means just first power, and R to the power n plus 1 is defined as R to the power n composition R. So it means, what is R square? R square is R composition R. What is R cube? It is composition of R square and R. And which can also be seen as that first we are taking R composition R, and then we are taking its composition with R, and so on. So to understand this, let us look at this example. We have to find the power of R to the power n, right? So to find the power of R to the power n, first I am calculating power of Rn. Suppose I first calculate R square. So what will be R square? It will be R composition R, right? So R composition R, how it will work? So we have the set, we have the relation R here, which contains the elements like 1 comma 1, 2 comma 1, 3 comma 2, and 4 comma 3. And I am writing R again so that you understand it easier. So here it is 1 comma 1, 2 comma 1, 3 comma 2, and 4 comma 3. Now what will be R composition R? So if you look at the first ordered pair, 1 is going to 1, and then again from this 1 will go to 1, so ultimately 1 will go to 1. Now there is no other element which is starting at 1 here, so I move to the next element, that is 2 comma 1. So 2 is going to 1, and here 1 is going to 1, so 2 will go to 1 finally, right? And there is no other element which is starting at 1, so now I am moving to 3 comma 2. So here we notice that 3 is going to 2 and 2 is going to 1, so 3 is going to 1. Here 3 is going to 2 and there is no other element which is starting at 2, so I am done with that. Now if I look at 4 comma 3, so 4 is going to 3, 4 is going to 3, and 3 is going to 2, so 4 will go to 2. So we have got the relation R square, which contains 1 1, 2 1, 3 1, and 4 comma 2. Now if I ask you what is R cube, so R cube will be R square composition R. Now look at this. We have the R element here, and so first I am taking R and then I will apply R square. So in the R we have 1 comma 1, so 1 is going to 1, and here also 1 is going to 1, so ultimately 1 will go to 1. Here 2 is going to 1, and here also 1 is going to 1, so 2 is going to 1, no change. 3 is going to 2 and 2 is going to 1. So here I will have 3 is going to 1. And here we have 4 is going to 3 and here 3 is going to 1. So ultimately 4 will go to 1. So there is a change over here, right? Now this is the composition r cube, right? If I ask you what is r to the power 4, then it will be r cube composition r. So let us do it again. R 1 goes to 1 and here also a 1 goes to 1, so 1 goes to 1. Here 2 goes to 1 and here 1 goes to 1, so here also 2 goes to 1. Here 3 goes to 2 and here 2 goes to 1, so 3 goes to 1. Here 4 goes to 3 and here 3 goes to 1, so we get 4 goes to 1. I hope you noticed one important thing, that we have got r cube and r4, both of them are same. So 1 1, 2 2 1, 3 1, 4 1 are the same. So it means that if I find any other power of r to the power n, it will be equal to r cube for all those values of n is equal to 5, 6, 7 and so on. Because r4 we have got is equal to r cube. So after that all other power of r like r5, r6, r7 will remain same. I would like you to verify this in case if you are feeling that it may not be so, right? Now there is one important theorem which you should know, that the relation R on a set A is transitive. The relation R on a set A is transitive if and only if R to the power n is a subset of R for n is equal to 1, 2, 3 and so on. So in case if I have to show that a relation is transitive, and if I have somehow shown that R square is a subset of R, then we can conclude that this relation is a transitive relation. So this theorem, I think you should try it, right? To try it, you have to understand that here you have to prove two things. First, you have to start that the relation R is transitive, and you have to show that R to the power n is a subset of R. Second thing, you have to show that you take R to the power n is a subset of R and then show that R is transitive. So I would request you to try to write the proof and comment in the chat box or comment section that whether you are able to prove this or not. Okay. Now the next thing that we are going to talk about is the matrix representation of the relation. Okay, so let's talk about it. So to understand the matrix representation, let us take this example. There is a set A and set B, and we have a relation R which is defined from set A to set B. Now what will be the matrix representation of this relation? So to represent it through matrix, first of all I need to have the elements of A, so which I am writing here 1, 2 and 3. So the elements of A I wrote over here, and what are the elements of B? The elements of B are 1 and 2. Now I look at this position. So actually this is a 3 row and 2 column matrix. So this will be a 3 cross 2 matrix. Why it will be a 3 cross 2 matrix? Because the number of elements in A are 3 and number of elements in B are 2. Now first position means first row and first column position will corresponds to the 1 1 entry. But in this relation we don't have the element 1 1, so I am going to place a 0. So the idea is that if that element is present, I will put a 1, and if that element is not present, I will put a 0. Now 1 comma 2 is also not present, so I will put a 0. 2 comma 1 is present, so I am going to put a 1 over here. 2 comma 2 is not present, so I am going to put a 0 over here. 3 comma 1 is present, so I am going to put a 1 over here. And 3 comma 2 is present, so I am going to put a 1 over here. So basically a matrix we have got like which has 3 rows and 2 columns, and the elements are zeros and ones, right? To understand it better, let us take one more example. Suppose I say that we have a set A which is having elements like A1 comma A2 comma A3, and we have another set B which has elements like B1, comma B2, comma B3, comma B4 and comma B5. Now suppose if I have to define a relation over A to B, so the relation is being represented by the matrix representation of it. And since the first set A has 3 elements, so it will have 3 rows, and the second set B has 5 elements, so it will have 5 columns, and the matrix looks like 0, 1, 0, 0 and 0. The second row is 1, 0, 1, 1 and 0. And suppose the third row is 1, 0, 1, 0 and 1. Now the question is that if this is the matrix representation, what will be the corresponding relation? So for our convenience, let us place A1, A2, A3 over here and place B1, B2, B3, B4 and B5 over here. So if I ask you that what will be the relation, so you can clearly see that A1 comma B1 will not be there because it is a 0 over here. A1 comma B2 will be there because we have a 1 in that location, and then A1 is not related to any other element, so now I can move to the next row. Now A2 is related to B1, so I am going to put A2 comma B1, and then A2 is related to B3, so I am going to put A2 comma B3, and A2 is also related to B4, so I am going to put A2 comma B4. And you have A3 comma B1, so I am going to put A3 comma B1 here. Then A3 comma B3, I will also put A3 comma B3, and finally I will put A3 comma B5. So I hope you have understood that given any matrix representation, I can write its corresponding relation, and given any relation, I can write its corresponding matrix. So this is how we can use matrix to represent a relation. There are two important observations that we need to have in mind. One is that if I am writing the matrix representation of a reflexive relation, then each entry along main diagonal will be 1. Why it is so? Because when I am talking about a reflexive relation over a set A, right, suppose we have a set A, and suppose for example I take element 1, 2, 3, and on this suppose I define a reflexive relation. So suppose I take 1, 1, 1, 2 and 2, 2, and suppose I take 2, 3, and then I take 3, 3. Now this relation is a reflexive relation because I have 1, 1 here, 2, 2 here and 3, 3 here. And if I have to write its matrix representation, you can clearly see that I will write 1, 2, 3, and here I will write 1, 2, 3. 1, 1 is there, so I will put a 1. 1, 2 is there, so I will put a 1. 1, 3 is not there, so I will put a 0. And then 2, 1 is not there, so I will put a 0. 2, 2 is there, so I will put a 1. And 2, 3 is not, 2, 3 is also there, so I will put a 1 again. And here 3, 1 is not there, 3, 2 is not there, and 3, 3 is there. So you can see that along the main diagonal, this element is 1, this element is also 1, and this element is also 1. So when we have a reflexive relation, its matrix representation will have 1 along the main diagonal, right? And if I have a symmetric relation, when I represent the symmetric relation through the matrix will be a symmetric matrix, right? I hope you all remember that a matrix, suppose I say B is said to be symmetric if B is equal to B transpose. So if I write the matrix representation of a symmetric matrix, then its transpose will be equal to the matrix itself. Okay. Now let us look at this example to understand it. The question is that if M is the matrix representation of a relation, then we have to decide that whether it is reflexive relation. So yes, certainly it is a reflexive relation because along the main diagonal we have 1. Now the question is it a symmetric relation? So to check whether it is a symmetric relation, you can clearly see that if I take the transpose of M, if I write M transpose, the first row here is 1, 1, 0, so the first column will be 1, 1, 0. The second row is 1, 1, 1, so the second column will be 1, 1 and 1. And third row is 0, 1, 1, so third column will be 0, 1, 1. And it is nothing but equal to the matrix M itself. So that is why this relation is a symmetric relation. Certainly it is not anti-symmetric, because the requirement for the relation to be anti-symmetric is that if we have some element like a comma b in R, then b comma a should not be in R. Yes or no? So here we can clearly see that if a comma b element is there, means this elements in for example ith row and jth column, if it is 1, then element in jth row and ith column should not be 1. It should not be 1, right? But here you have seen that element in the second row and first column, means if I call this position 2 1 position, I hope you understand this, second row and first column, right? So this is element in you can call it element in second row and first column. And if I look at this element which is there in the first row and second column, both are equal to 1. So that is why it is not anti-symmetric. So we have just seen the matrix representation of a relation. Relations can also be represented through a directed graph or digraph. So let us talk about how to use the directed graph or digraph representation of a relation. So here we have an example which I have defined, or this relation is defined over the set 1, 2, 3, 4. So I am saying that this is element 1, we have element 2 over here. Let us take that this element is 3 and this element is 4. I think by now you might not be aware about directed graph. When we talk about graph in discrete maths, we are talking about a structure which has certain number of vertices and then the edges join those vertices. So first of all, if I see this relation, we have 1, 1 element, means 1 is related to itself. So we are going to draw a loop over 1, means 1 is related to itself. Then 1 is related to 3, so we are going to draw a directed edge from 1 to 3, which is like joining 1 to 3. Then 2 is related to 1, so I am going to draw a directed edge from 2 to 1, and you look at the arrow, the direction of the arrow, because the 2, 1 is there, so it is pointing from 2 to 1. Now 2, 3 is there, so I need to draw this directed edge because it is pointing from 2 to 3. Now 2, 4 is there, so there will be an edge between 2 to 4, and here this edge looks like this. 3, 1 is there, so I need to draw another edge 3, 1, and it will point in this direction. 3, 2 is there, so I need to draw this edge 3, 2, right? And 4, 1 is also there, so I need to draw an edge between 4 and 1, and this is how it will look like. So this is the directed graph representation of the relation, right? There are few important observation. I think you are smart enough to make that if I talk about the directed graph representation of a reflexive matrix, so a relation is reflexive if and only if there is a loop at every vertex with the directed graph. Because suppose I take an example and I say that we have a set which contains 3 elements 1, 2, 3. And suppose we have a reflexive relation over this set A. So if it is reflexive, certainly every element will be associated with or related to itself. So there will be loop over every element. So that is what they are saying, that in case if a relation is reflexive, then there will be a loop at every vertex of the directed graph. Now if the graph is symmetric, if suppose I say that this element is 1, this element is 2, and this element is 3. So if 1 is related to 2, then 2 must also be related to 1. So for every edge between any two vertices, like if there is an edge from 1 to 2, and if the relation is symmetric, then there must be an edge between 2 to 1, right? So that is the requirement for the relation to be symmetric. Similarly, if I say that a relation is transitive, it means what? That suppose I say that we have such possibility that 1 is related to 2, so there will be an edge between 1 to 2, and 2 is related to 3. So suppose I say that 2 is related to 3, so there is an edge between 2 and 3. Then in that case, the 1, 2 element is there and 2, 3 element is there. So for this to be transitive, 1, 3 element should also be there. So this edge should also be present in the graph. So that is what they are saying, that if a relation is transitive, if and only if whenever there is an edge from a vertex x to a vertex y, an edge from vertex y to a vertex z, then there must be an edge from vertex x to vertex z. And what about anti-symmetric characteristic? Anti-symmetric characteristic is that if a comma b is there, if a comma b is in R, then b comma a should not be in R. So because of this requirement, if the relation is anti-symmetric, and suppose there are three elements over which I have defined it. So suppose there is an edge between element 1 and 2, then there can't be an edge between 2 and 1. So there will be certainly not an edge between 2 and 1. If there is an edge between 2 and 1, then it will not remain an anti-symmetric relation. Yes or no? Similarly, if there is an edge between 2 and 3, then certainly there should be no edge between 3 and 2. Right? So right now it is anti-symmetric, but suppose I join this edge also between 3 and 2. So now it is not anti-symmetric. Okay. So I hope you have understood that the relations can be represented through different ways. One way is to list down all the ordered pair, right? Another way is to use the matrix, and third way we have discussed is the representation through directed graph. So we can use the directed graph representation of a relation as well. So, I think we have discussed a lot of things in this video. I hope you have liked the video, you have enjoyed the process, and in case if you feel like that others should also get the benefit of this, you must share it with your friends as well. And my request again and again is that try to watch the videos in sequential order and watch from beginning to end. Don't feel like that you will learn everything in just few seconds or few minutes. If you want to get your concept right, then you must watch the videos in detail. Whenever if you are not understanding something, pause the video, go back and then again watch it. In some situation it may happen that you are understanding the thing, then you can increase the speed, you can watch it at 1.5x speed. So certainly the process should be enjoyed, and you must learn the concept clearly. So that's all from my side in this video. Thank you and have a great day.